Thank you. So I'd like to thank the organizers for inviting me to give these two talks. And it's always great to be at MSRI. It's a wonderful place for to visit and to speak. Beautiful boards. So I'm going to be speaking about hopf algebras, and I'm viewing this as their action. I'm going to be talking about their actions on rings, their actions on modules, what types of categories their modules form, and I'm really viewing this as a generalization of group actions. So groups act on rings, on sets, and so on in a particular way, and they act by symmetry groups. Hopf algebras act as well, and we can think of that as being quantum symmetry. So that's one of the strands. So I will start at the beginning. I'm not going to give a complete definition of Hopf algebra because it involves so many diagrams that are not so illuminating until you see where they come in. So I will be pointing out where they come in when needed. But let me just give a basic setup. So Hopf algebra is an algebra A. And let's say over a field that I'll write as K. It could be over a commutative ring, but I need to be a little more careful about some things. So I want to work over a field together with K-linear maps. Delta will map A to two copies of itself, A tensor A. And I should write over here that by tensor product, I mean over the field, unless I write it otherwise. There's a map epsilon from A to the field. And there's a map S from A to itself. And these maps are all required to satisfy some properties. So, and those are the properties that, as they come up to be used later on when I talk about something that they're used for, then I'll mention them. But I won't write them down here. Let me just say delta and epsilon are both supposed to be algebra homomorphisms, and S is an anti-algebra homomorphism, reverses the order. But again, the other properties will come up, and I'll explain them. So this is the basic idea. Maybe I should also write delta is called co-multiplication. Epsilon is called co-unit or antipode. Or, sorry, augmentation. S is called co-inverse or antipode. So these are best explained by showing examples. So some of the main examples, or some of the first examples, are these. Group algebra. So let's say G is a group. And KG is a group algebra. And what are these maps? Delta takes a group element to two copies of itself. Delta of little g is G tensor G. Epsilon takes a group element to the identity in the field. And S takes a group element to its inverse. And then these are K-linear maps, so you extend to the rest of the group algebra using that property. So this is one of the first examples. Another standard example is universal enveloping algebra of a Lie algebra. So G is a Lie algebra now. So I'll give an example. If you haven't seen this before. But let me just first say, in general, for this algebra, delta of x is equal to x tensor 1 plus 1 tensor x. Epsilon of x is 0, and s of x is minus x. For all elements of the Lie algebra, and then you can extend to maps on the whole universal enveloping algebra by the property that these should be algebra homomorphisms. And the Lie algebra elements generate the algebra. Oh, yes, I was going to give an example. So for example, U of SL2. Okay, so by SL2, let me just put that here. This is 2 by 2 matrices of trace 0.
So
Yes.
identical 0?
Oh, good question. Okay, you mean for the Lie algebra. So the co-unit, this is supposed to be an algebra homomorphism. So the identity element of the algebra, the multiplicative identity, goes to 1, always. And so the co-unit takes the generators to 0, but maybe I should say there's an identity element that's always taken to 1. Yeah, so the co-unit is not identically 0, but it's 0 on the generators. Yeah. Yeah, thanks. Uh-oh. Oh, thank you. Did I say that and I forgot to write it? I hope. Okay, thank you. Okay. Yeah. All right. So 2 by 2 matrices of trace 0. So basis, because I want the notation, let me just say E is going to be the element 0, 1, 0, 0. F is going to be the element 0, 0, 1, 0. H is going to be the element 1, 0, 0, negative 1. Okay, so regardless what the field is, these matrices make sense. And those are going to be a basis for 2 by 2 matrices of trace 0. The universal enveloping algebra is an associative algebra in which this embeds in a particular way, so that commutator bracket corresponds to the bracket on the Lie algebra. Or the commutator bracket here corresponds to the bracket on the Lie algebra. The algebra structure, this can be described as generated by E, F, and H. Subject to relations EF minus FE is equal to H. HE minus EH is equal to 2E. And HF minus FH is equal to minus 2F. So you can describe this as an algebra with generators and relations this way. It comes from the algebra structure on 2 by 2 matrices. Okay. So this is, these generators, E, F, and H, have this co-multiplication, this co-unit, and this co-inverse structure. Okay, so those are some classical examples. In the 1980s, there were some new examples given by quantum groups. So let me define some of those. So I'm going to take, again, a Lie algebra such as SL2, and I'm going to define an algebra that's similar to this one, only I have a parameter Q. So maybe I should say Q is going to be an element of the field, and it's not plus or minus 1 for what I want to do with it. Sometimes other restrictions are put on that parameter. Okay, so this is a quantum group. And I will just give an example because there's a lot of notation that I don't want to introduce in general. But let me just give one example, UQSL2. So this is the algebra generated by capital E, capital F, capital K, and its inverse, subject to relations EF minus FE is equal to K minus K inverse over Q minus Q inverse. Okay, this should be a invertible element, non-zero. KE is equal to Q squared EK, and KF is equal to Q to the minus 2 FK. There are some slight variations on this that you might see in the literature, but that's a basic example. And this should remind you of the structure over here. The K is an exponentiated version, that capital K, is an exponentiated version of this little h, and that can be made precise. So the original structure really does come from SL2, but this is how this is defined, by generators and relations. Okay, so that's the algebra structure. I need to tell you what is the co-multiplication and so on. In other words, the co-algebra structure. So delta of E is E tensor 1 plus K tensor E. Delta of F is F tensor K inverse plus 1 tensor F. And delta of K plus or minus 1 is K plus or minus 1 tensor K plus or minus 1. So the K is behaving like a group element. And the E and the F are behaving sort of like Lie algebra elements, except that you have a little bit different structure for the co-multiplication. Let me say, so epsilon of E is 0, epsilon of F is 0, epsilon of K is 1. And there's an antipode structure which is almost the same as this one, but you have extra copies of group elements in there, and I don't want to write that down. But it can be worked out. Okay, so this is an example of a quantum group, and this structure generalizes to other Lie algebras, semi-simple Lie algebras, with a little bit more notation. So another example that is important for what I want to do later is a small quantum group. So I have a small u, small quantum group. And this is defined for roots of unity. Let's say Q is a primitive nth root of unity. So this can be defined in various ways, but I'll just define it as a quotient. For example, little uq of SL2 is defined to be big uq of SL2 modulo the ideal generated by, okay, here's the n. Q is a primitive nth root of unity. I want to mod out by the power of e to the n, f to the n, and k to the n minus 1. Mod out by that ideal. So that becomes a finite dimensional Hopf algebra, finite dimensional as a vector space. And I'll be interested for some of what I want to talk about, I will be interested in these sorts of finite dimensional Hopf algebras. The co-multiplication and so on is just coming from the original infinite dimensional capital UQ SL2. And this can be generalized to other Lie algebras. Question?
Sometimes people do K to the 2n there instead and also call it the same thing. Is there any standard or is it just?
Yeah, it depends on your choices. Yeah, that's right. Sometimes you mod out by, sometimes you take K to the 2n. It just depends on your choice. Yeah. And there's also the parameters too. I mean, sometimes the Q is replaced by Q squared and in other contexts. Yeah. So if you're reading paper, you just have to be careful you get what they wrote down. Any other comments? Okay. So these are, yeah, there are a lot of examples that are similar to this, have a little bit different relations. So these are just some examples. I'm going to need some notation for the coproduct called Sweedler notation. So let me write that down now. For the co-multiplication, or sometimes called coproduct. Okay, let's let A be an element of our Hopf algebra, capital A. The coproduct, or the co-multiplication applied to that element, is in A tensor A. So we can write it as a sum of a bunch of pure tensors. The notation that Sweedler introduced is this. I'm going to write it as A1 tensor A2. And this sum is over some set of indices, which I'm not writing down the indices. So this is the Sweedler notation. So this is a symbolic notation. Some prefer to use indices indicating which sum you're in. But that gets a little bit tedious because sometimes you want to apply this twice. And one of these properties over here is co-associativity. So the co-associative property of a Hopf algebra is that if you apply this again to either one of the two tensor factors, you get the same thing, doesn't matter which way. So if we apply delta and then we apply delta tensor the identity map, that's the same thing if we apply delta and then we apply the identity map tensor delta as maps from A to 3 copies of A tensor A tensor A. Okay, so this, for a Hopf algebra, we've got a co-associative co-multiplication. And in this notation, if we want to do this again, we will just write some A1 tensor A2 tensor A3. And the sum is over some indexing set, finite. But if I really used indices to indicate which sum in, then that would make this really messy. And if you want to apply it 4 times or 5 times, then it just gets out of hand. So that's the notation. I will be using that. It takes some practice to get used to using it, but that's the notation. Okay, so I said Hopf algebras act on rings. Let me talk about actions on rings. Okay, so for actions on rings, I really want to start by going back to the beginning. What is a group action? What is a Lie algebra action? And go through these examples because I think it's helpful to see the generalization. So groups act by automorphisms. So suppose we have a group G and we want it to act on a ring R. So group G acts on a ring R. By automorphisms, so what we mean by that is G acts on a product R prime this way, pointwise. G acts on R, G acts on R prime, and we're multiplying. Okay, that's what it means to act by automorphism. Also take the identity, maybe I need to write this down too. G takes the identity to itself. Acts trivially in the identity element. Okay. So I want to compare that with the coproduct on G, little g, which is G tensor G. And the co-unit on little g is 1. So if you compare that, this G tensor G corresponds to those 2 copies of G, and this 1 corresponds to this 1. Okay, so let me do this for Lie algebras. Lie algebras act by derivations. So if you have a Lie algebra G, it acts on a ring R. An element of the Lie algebra acts on a product this way. X acting on R prime is X acting on R times R prime plus R times X acting on R prime. Okay, that's how Lie algebras act. That's compatible with their structure. And I want to compare this to the coproduct for Lie algebra. Delta of X is equal to X tensor 1 plus 1 tensor X. Epsilon of X is 0. Oh, I forgot to write that down. X acts on the identity element of the ring as 0. So if you compare the coproduct on the Lie algebra element to this equation showing how it acts as a derivation, you've got the X tensor 1 and 1 tensor X corresponding to the coproduct. And the epsilon of X equals 1 is corresponding to how it acts on the identity. So group acting by automorphisms or Lie algebra acting by derivations, that structure, the automorphism or the derivation, really is I want to see it as corresponding to the co-multiplication and the co-unit for each of those examples. So let me define in general then a Hopf algebra action on a ring. The properties that we want it to have. So more generally, here's a definition. Let A be a Hopf algebra and let me take another K algebra. Let R be a K algebra. Then R is an A module algebra if. Okay, several things. First of all, it should be an A module. Okay, so let's say left A module. I've been writing left actions. So we want it to be an A module. So A is acting on the ring, but think of it as a vector space. We've just got an A module. And the next 2 properties have to do with the additional structure. 2, A acting on a product R prime is equal to the sum A1 acting on R times A2 acting on R prime. Okay, so here's where I wanted to use Sweedler notation to express this property. Okay. So the action on a product is really corresponding to the co-multiplication of the elements in the Hopf algebra. Okay. And 3, something about the identity. A acting on the multiplicative identity for the ring or the algebra is epsilon of A times, that's a scalar. So I just multiply by the identity element. And this is exactly what we have up there for a group in a Lie algebra. Well, okay. The group, we extend the action to the group algebra. The Lie algebra, we extend the action to the universal enveloping algebra. So the examples. Group algebra, universal enveloping algebra, Lie algebra, as above. So these actions can be extended so that you get modules for the corresponding algebras. And then they fit this definition. You've got A-module algebras. Any question? So I'll give a different example. I want to give this example. So this is more classical, the actions of groups by automorphisms, actions of Lie algebras by derivations. The quantum group example is a little bit newer. I'll put that down. Not that new at this point, but it's a different type of example. So maybe I'll put it here. Let me take the hopf algebra to be that one, UQSL2. Maybe the one number 3. And I want to take the algebra to be the quantum plane, which is defined as an algebra given by generators in relations x and y, such that xy is equal to qyx. Yeah. So q is just some scalar. This is sometimes called the quantum plane. Because if q is 1, you've just got polynomial ring. And you can think of that as an algebra of functions on the plane. So we'll call this the quantum plane as a quantum analog, Q analog. Okay, the action that I'm interested in is this one. E is going to act on x as 0 and on y as x. F is going to act on x, takes it to y, takes y to 0. K is going to act on x to be qx, and it acts on y to be q inverse y. Maybe I should put plus or minus 1. And you can check that this satisfies the definition once you extend. So this extends in such a way that R is an A-module algebra. Okay, which requires some checking because so part of this is being used to extend the action. We need to check, though, that this relation is preserved. And in order to do that, I'm not going to do it, but let me just say, E and F end up acting as skew derivations. So by skew derivation, so derivation, by definition, is a function that acts on a product this way. A skew derivation is almost the same, but there's a group action that shows up in the middle. So, for example, E acts on a product R times R prime. So here's where I'm going to cheat and look at the coproduct for E, or the co-multiplication for E. This is going to be E acting on R times R prime plus K acting on R times E acting on R prime. So the action on a product of two elements comes from, or corresponds to the co-multiplication of that element. And if you use this definition, you can check that this relation is really is preserved by the action once it's extended to the whole algebra. Okay, so what is a skew derivation? A skew derivation is just like a derivation, except in one or the other component, you replace the identity element by a group element acting on it. So you have an automorphism here. Or you might have it in this position, or both. Okay, so this is the type of action that I'm interested in. Hopf algebras are acting on rings. You end up getting more general types of actions then than the more classical ones coming from groups or Lie algebras. There are some important constructions that come out of this. So let me define the invariant ring. So when you're interested in group actions, you're sometimes interested in the invariance of the actions, right? So let me define that more generally in the setting. So there are a couple of rings that I'm interested in that coming from an action. So there's the invariant subring. So I have my Hopf algebra A acting on my algebra R. Invariant subring I'll indicate that way, and it's defined to be all the elements of R for which the action is trivial in the sense that A acting on little r is epsilon of A acting on, multiplied by R. So this is what I would call a trivial action. And this is defined as the invariant subring. If this is a group action, those are going to be all elements that are just taken back to themselves by the group action, right? So this is a generalization of that. There's also the smash product ring. So this is going to be a bigger ring, R smash A. This is defined to be the tensor product of R with A as a vector space. But then I have to tell you what the multiplication is. So the multiplication uses the action. If I want to multiply two elements of the form R tensor A and little r prime tensor little a prime, so I could just multiply the r and the r prime, the a and the a prime. But I want to change that a little bit. The a is moving over the r prime in order to be multiplied by the a prime, and I'm going to apply the action when I do that. So this should be the sum of r times a1 acting on r prime, tensored with a2 times a prime. And the sum is over A, in other words, we're taking the coproduct on A, and so we're summing over that, what we need to for the coproduct on A, or the co-multiplication on A. Okay, so that's the smash product ring, and this is a really useful ring. It encodes the ring structure of R, the Hopf algebra, the structure of A, and also the action itself. So it's got everything all in one place. And it turns out that a lot of rings really do have this structure, or maybe are deformations of something of that form. So let me just give examples that we've already seen. So one example we could call the Borel subalgebra. Of UQSL2. So what do I mean by this? By analogy with classical Lie algebras, I'm going to look at sort of the upper half of that structure. I'll just take E and K. So this is going to be the subalgebra generated by E and K. And maybe I can write it this way, K plus or minus 1. Subject to the relation KE is equal to Q squared EK. Okay, so I just skip taking the generator F, and I have everything coming from the generators capital E and capital K. And this turns out to be isomorphic to smash product. This is polynomial ring in E, smash product with the group generated by group algebra of the group generated by K. Maybe I'll write it this way. This is the group algebra of the free abelian group, free group generated by K. And this is a polynomial ring. Okay, but that really is a smash product. Kx on E can extend to action on the polynomial ring, and this is what you get. So this is underlying, the smash product structure is underlying that example and many other examples of Hopf algebras that we're interested in. And in fact, the example itself, UQSL2, can be considered a deformation of a smash product ring. And deformations are also of interest. So let me write that one down, because that may come up later. So in fact, UQSL2 itself may be viewed as a deformation I'm not going to define right now, a deformation of a smash product ring, polynomials in E and F. Consider the action of the free group generated by K on that given by powers of Q. And you can form the smash product. The only thing that's different from the smash product in the original definition UQSL2 is E and F commute here. Right? E and F commute if you're talking about a polynomial ring. And over here they don't commute, but they don't commute in a particular way, right? The difference of EF and FE is just something coming from the group algebra of K. And if we think of that as being maybe in lower degree, we can take a PBW deformation. That's another term that I'm not going to define now. We can get the quantum group back from this. So there's a way to view some of these Hopf algebras as deformations of simpler ones in some sense, of simpler algebras. And that turns out to be a useful way to view them sometimes. Okay, so those are Hopf algebra actions on rings. I want to step back a little bit and talk about hopf algebra actions talk about their modules and what structure their modules forms, because we're going to get tensor categories, and these are very important, and they're going to come up in other talks in this workshop as well, particular types. So let me talk about that. So again, I'm going to take A to be a hopf algebra. And I'll let U and V be A modules. So those are going to be vector spaces with action of A. Then U tensor V is a module via the co-multiplication delta. So let me just write down explicitly elements. Little a is going to act on little u tensor little v as the co-multiplication would specify. A1 acts on u, A2 acts on v. So the action on a tensor product is given by the co-multiplication. Okay. So that's another A module. So that's great. We also have the field itself as an A module. Okay, the field itself is an A module via the co-multiplication. Via the co-unit. So A acts on the multiplicative identity of the field as epsilon of A multiplied by 1. Well, just epsilon of A. So that's an A module. We also have a dual module. So let me define U dual. This is a dual vector space, but let me write it down so that we have it. This is the dual vector space. All k-linear homomorphisms from U to K. K is the field. So this is an A module via the antipode or the co-inverse in this way. So let's see. I want an element little a of A to act on a function, f. Give me another function that I'll take little u to something, and it should take it to f of s of A, u. So A is an element of the algebra, capital A, little u is in capital U, and f is a homomorphism. Antipode, the co-inverse is an algebra anti-homomorphism, so that's why this works. You need to use that property. Okay, so we have a dual object, a dual module, and these modules have some properties. These structures have some properties that are very important. So one is that if you take a tensor product of 3 modules, it doesn't matter. The order matters, but the parenthesization does not matter. So U tensor V tensor W is isomorphic to U tensor V, in parentheses, tensor W. And this is by co-associativity of the co-multiplication. Okay, so that's very important. We get this sort of associativity up to isomorphism of this structure. Second property, if we take, so K is the field. If I write it in the context of a module, I mean that module structure that I wrote up there. K tensor U is isomorphic to U is isomorphic to U tensor K. And this is by another property that I didn't write down, but I'll write it down now. So we require the co-multiplication and the co-unit to interact in a nice way, and that is that. If you apply the coproduct to an element, and then you apply the co-unit to one or the other factor, you get back where you started. That's equal to A. So this is what it looks like in Sweedler notation. And it gives you exactly this property that the so-called trivial module, the field as a module, tensored with any other module, it's behaving like a multiplicative identity for modules. Right? Okay, so these are very important properties. Maybe I should say there's a property for the dual. Maybe I have space to write it. So if U is finite dimensional as a vector space, then the composition U goes to U tensor U dual tensor U goes to U is the identity map. I have to tell you what those maps are, though. So this first map is going to be the so-called co-evaluation map tensored with the identity. And the second map is the identity tensored with the evaluation map. So the co-evaluation map, and maybe I should say that I'm making some identifications here that I should be a little clear about for the notation. U is isomorphic to K tensor U. And this is the notation that I want to identify these in order to make sense of this map. Co-evaluation map on the identity element of the field takes it to, okay, so I do need some indices here. U sub I tensor U sub I star. So these are dual bases. Assuming I've got everything in the correct order. Yeah. So you choose a basis for U and the corresponding dual basis for the dual vector space. And this is the co-evaluation map. The evaluation map is easier to write down, and it's what you would think. The evaluation map takes a function tensored with an element, and we're just applying. So this turns out to be true. This composition is the identity map. And there's a similar, well, maybe I'll say that in a minute. Okay, so these are very important properties of modules for a Hopf algebra, and they're some of the properties that you need to be able to say that you have a monodic category or tensor category. So let me write that down next. A tensor category, or monoidal category, is a category C together with a functor that I'll call tensor product. So in my hopf algebra examples, it will be exactly the tensor product we've been using. In general, it could be any functor with the right properties, from C cross C to C. An object that's often written as a boldface 1 in natural isomorphisms U tensor V tensor W isomorphic to U tensor V tensor W with the parentheses in the other position. 1 tensor U is isomorphic to U is isomorphic to U tensor 1. And this is for all objects. U, V, and W in C. So that's the basic idea. What I have written over here shows that we get the structure and the category of modules for hopf algebra. So let me write that down. So example. C is the category of modules, and sometimes we want to specify finite dimensional modules for a hopf algebra A. So if I restrict to finite dimensional modules, meaning finite dimensional as vector space, then we have this additional property. There's the yellow chalk. So maybe I should put over here, K, the field as a module is 1, right? That's boldface 1 for the category. So we have a tensor category, a monoidal category. We have this additional structure, in fact, for finite dimensional modules. Let me put it over here. Under the assumption that the co-inverse S of A is invertible, meaning a bijective map, then we have some additional structure. So maybe I should say this is always true for finite dimensional hopf algebras. Meaning finite dimensional as vector space. There are other notions of dimension that are important, so I just mean as vector space here. Assuming the co-inverse of A is invertible, then we really get, then C is a rigid monoidal category. And the rigidity is the additional property given by the dual. Maybe I should say that for that terminology, we want to also assume there's another dual. So let me put this down. So this is called a left dual. This is called a left dual. And my notation is from the book EG&O, Eddinghoff, Gilaki, Nikschitz, Ostrich. The opposite notation is used in Bakalov, Kirillov, I believe. So you have to be careful which way you put your star. But In any case, I'm calling that a left dual. That's the notation for left dual. There's a right dual in this case where you list the asterisk on the other side. And this is also, as a vector space, it's the dual vector space, but the action is different. So the action of A on a function here applied to an element of U is f of S inverse of A applied to U. For rigid monoidal category, you're asking for both left and right duals, and both have a property, this property. There's an analogous one for the other dual. Okay. So that would be a rigid monoidal category. So the category of modules for a Hopf algebra generally has this property. It's a tensor category, maybe with some additional structure. So we're often interested in braided categories. So some Hopf algebras have categories of modules that have some additional properties. They might be braided. They might be semi-simple. Semi-simple Hopf algebras have semi-simple categories. They might be braided. So braided would be, where's my tensor product? So I've said the tensor product is associative up to isomorphism, tensor product of modules, but I haven't said that it's commutative up to isomorphism. If you wanted to be commutative up to isomorphism, and there are very important examples like the quantum groups that I mentioned, then that's an additional property and corresponds to having a braiding, and that's a very important structure that will come up in some of the other talks. So let me just end by saying what I'm planning to do next. So I've really just introduced Hopf algebras and their actions and their categories of modules, the properties that they have. I want to talk next time, which is on Wednesday, a little bit more about some recent research and some techniques for understanding the structure of Hopf algebra, structure of their modules, particularly in the non-semi-simple case using homological methods. So that's mostly what I'll focus on next time. And I'll be focusing particularly on pointed Hopf algebra, so I'll define those and define the homological techniques that I'm interested in. And we'll be using a lot of what I introduced today. So thank you. Okay, I guess I'm sorry, I'm not sure I understood the question. For finite group, right, A is the group algebra of G. So a representation of the group would be the same as a module for the group algebra in the way I was viewing it. Was that the question? Yeah. Right. And so the same for Lie algebra. So Lie algebra, so there are modules for Lie algebras that extend to modules for the universal enveloping algebra. And so I'm viewing all of this in this larger context of algebras. Yeah. Thank you.